My name is Michael Gopshtein. I work for Eyeway Vision, where we create augmented reality glasses, the next generation of the glasses, and we believe that eventually AR will replace all other devices, all other displays. And we use CUDA to accelerate algorithms on GPU devices, especially for computer vision algorithms. And basically, what is CUDA? It's a platform by Nvidia which allows you to create applications and algorithms which will run on Nvidia GPU devices. And it's heavily used for algorithms, like we said, like computer vision, but also for machine learning, simulations, and other high-demanding algorithms. And it contains support for different languages. It comes with a set of tools like the compilers, debuggers, profilers, and also with a set of libraries which you can start using out of the box. And we will be focusing on CUDA C, C++. I'm not going to do a deep introduction into the CUDA C, C++, but even if you're not familiar with it, I will explain all examples, so it should be easy to follow the session. So we'll use like the hello world example for CUDA algorithms. It's an addition of two vectors. We have vector A and vector B, and we want to create a vector C, which is an element-wise sum of the vectors. And this operation, it has a nice property that we can calculate each cell in C independently of other cells. And then with CUDA, we'll assign each cell in C a separate CUDA thread, which will handle the calculation, and then we'll span out many such CUDA threads, and hopefully we'll complete the calculation faster. Now, the term CUDA thread is not exactly like a thread that you may be used from stud threads and or from operating systems, but for the sake of the session, the analogy is good enough. So the way you express it with CUDA C, C++, is that first you create a function. In this case, it's add kernel, which runs on a GPU. And you have to start it with special keyword global, but otherwise it looks like a regular function. It has all the parameters, right? The vectors C, A, and B. And in the first line in the body, it calculates the index which it should operate on. And we will not talk about these block indexes and thread indexes. What's important is that each CUDA thread will get a unique index into the data. And then in the second line, we do a regular calculation of some of the vectors. And this part of the program which runs on the GPU is referred as a device code or kernel. And again, just not to be confused with kernels that may be used on Linux and so on. It just means that that's a function which runs on the GPU and is launched from a CPU code. And in the second part of this example, we launch the kernel using the special triple angle brackets syntax. And we are not going to talk about the parameters inside, but otherwise, it looks like a regular function call. We pass the parameters in, and the function starts running on the GPU. And this part is called a host or a CPU code. And also, you can note the tags on the left side, which mark which part of the code runs on device and which runs on host. I will use like the same color tags in this presentation to make it easier to see which parts run where. But now the question is, like this example is a pure C example, and where are all the pluses of the C++? And what I found out that in most of the examples that you find on the internet and even in books, especially the basic examples, they're all pure C code. And what I want to show is how you can use like standard C++ features in CUDA and make your code safer, more readable, and maybe even faster. So we'd like to start our journey from CUDA C programming and hopefully find a path to better code. I just want to mention that there are different ways to use C++ with CUDA. So one of them is Thrust, which ships as part of the CUDA package. And on top of OpenCL, you can use SQL. And there are also OpenSCC, OpenMP extensions, which are basically annotation-based extensions to C++. So I'm not going to talk about how you decide which one you want to use, but given that you're using CUDA C, C++, and you're creating your own kernels, I want to show which features of C++ you may want to use. Going back to the definition of the function, in the current form, it operates on integer vectors. But what if we would like to sum up float arrays? Then the C solution is very simple. We create another function with a different name, let's say @kernel f, and now the parameters are floating points, but otherwise the body is exactly the same. The C++ solution is much simpler. We define the kernel function as template, and we use t stars arguments in the function signature. And then when we launch the function, we can either use an explicit syntax of instantiation to int, or we can skip it, and the template parameters will be deduced automatically. It works like in the regular CPU code. I mean, it's a very basic feature of C++. It may not be very exciting, but just shows that you can use it with CUDA kernels as well. So the second aspect of this function signature that we want to address are the pointers. So what's exactly the memory these pointers are pointing to? In the CUDA system, basically there's a CPU with a CPU memory or a host memory, which is the usual memory that we use in all our C++ programs. And then each GPU device comes with its own memory. And the kernels which run on GPU may only access directly the memory of the device. So what we usually do in CUDA programs, we first allocate a memory on a device with some CUDA malloc call, and then we copy the data with CUDA memcopy. So in this example, we would copy vectors A and B from a CPU to a GPU, then we'll launch the kernel, and then we need to copy the results back from the GPU to a CPU. Now this is an example, very simple code, which launches our original kernel, but in this case, we send it a pointers to local int arrays. And the main problem with that code is that it compiles, but it fails in runtime. And of course, in C++, we would like to capture all the errors as early as possible, and we want to leverage the type system to avoid these errors in the compile time. So what we may like to do is to replace raw pointers with special type of device pointers, which basically explicitly indicate that this memory resides on the GPU, and it's safe to access it from kernel code. And so we want to create a helper class like with device PTR, which basically it stores the raw pointer inside, but then the constructor from the raw pointer is marked as explicit, and then you should explicitly say that you know that this pointer is safe to be used in GPU code. You can also note the special keywords like __ device, which means that this function can run in the GPU context. And basically, all the functions, free functions and member functions, which are invoked from other methods on the GPU, should have this device keyword. You can also add a helper function, a convenience function, which would take a t pointer and would make a device PTR from the pointer. And then we can use the classes. Like in this example, we can have a process function which gets the pointers to the input data and the pointer to the place where we want to store the result, the C. And then we start from A. We allocate a memory on the GPU with CUDA malloc. Then we copy the input memory of A to the GPU with CUDA memcopy. And you may note the last parameter to the function, it's CUDA memcopy host to device. So we need to specify which direction the copy is. Either it's from host to device or from device to host. And then we'll do the same for vector B, and we'll also allocate a memory for vector C. And now we can launch our kernel, and instead of using raw pointers, we would use make device PTR call, and now the call is safe. And when it's finished, we want to copy the memory back of the resulting vector C and free all the arrays on the GPU. Maybe even a simpler way of doing this code can be this. So we assume that we have some device memory helper class, which can allocate a memory for us and also release the memory in the destructor. And then a special copy elements function now doesn't need to get a special parameter of the copy direction as a parameter. It can be just deduced from the type of the arguments. Right? If we're copying from the pointer in the CPU to a pointer in the GPU, then we can deduce that the direction is host to device. So we can create a device memory class also in a pretty similar way. In this case, we can make the constructor private and add static functions which explicitly would define whether we allocate elements or bytes. I think just for readability, if we have a device memory class of type T, we just have a constructor which gets size as parameter. It's not clear if we're talking about bytes or number of elements. So I would prefer to make it explicit. And in the destructor of this class, we would free the memory. And we can also add a conversion operator to a device pointer. OK, so going back to device pointer, there are certain properties of the pointer which we want to have. For example, we want to allow the conversion of int pointer to a constant pointer, but not the vice versa. And also, we don't want to allow a copying of pointers of different types. So basically what we say, we want to allow a copy of device pointer of type T had to device pointer of type T, if and only if the T1 pointer is natively convertible to a T pointer. And we can easily express it in C++. So we create the constructor to a device pointer which takes device pointer of type T1, but we only enable it if the types of the pointer are convertible. And again, it's not a very exciting piece of C++ code, but it just shows that you can use all the SFINI and all the type traits in the GPU code in the same way as you do in the CPU code. And we can also use it for static polymorphism. So in this example, we create a functor class, the binary op plus, which defines which operation we want to run on our vectors. In this case, it implements a function call operator and just performs the sum of two elements. And our kernel function can be made template by the type of the operation we want to invoke. And when we launch the kernel, we'll specify the name of the of a struct which we would like to create on the GPU. And then we can customize the performance of our kernel function. OK, so we've seen a way of doing static polymorphism with templates. The next stop is dynamic polymorphism. And so now we have an interface, a binary op interface, which defines an abstract function call operator, which operates on two elements of type T. And again, we want to add an implementation of this interface, binary op plus, which does the sum of the elements as we expect it to do. And now, on device side, we can have some worker function, which basically gets all the vectors A, B, and C, and also gets a reference to an interface. And inside, it will use the interface via the virtual function, and will call the correct operation of the provided implementation. And now our add kernel function can create an instance of binary op plus inside and just invoke the worker function. And that's fine, but you may note that both the add kernel and worker functions, they all run in the context of the GPU. And basically, you're not allowed to pass a parameter with virtual functions when you launch a kernel. And it makes sense, right? As the classes with virtual functions, they probably have some pointer to virtual table, which is located in the CPU memory, and then it's not accessible from GPU memory. But the business logic, which wants to decide which of the operations we invoke, it usually resides on the CPU. So I want somehow to be able to send. Okay. So one way that we can solve it is, as we did in the previous example, we can just add a template parameter to our kernel function, instantiate it to binary op plus, and then our kernel function will create the object of the correct type, which implements the interface, and we run the worker, and that's fine. But there is a design problem, as if we already have this parameter as a template parameter, then there's no point to convert it later in processing to the virtual function. So instead, we'd like to do something like that. We'd like our add kernel to have a parameter which is of a type of a pointer to an interface, so binary op, and somehow in our CPU code, we would like to create this object in a GPU namespace. So our strategy to solve that issue would be this. So first, we would allocate the memory on the GPU, as we usually do. Then on the GPU side, we would initialize the memory to the correct type of object T. And now on the CPU, we have a valid T pointer in hand, and we can use it to launch the kernel. So we can build this dev object, helper class, which will do the work for us. So it has the memory with the help of dev memory class, which you've seen before. In the constructor, it will first allocate one element of type T, which means just the raw memory of the appropriate size. And now we want to construct the object. So what we would like to do is basically to run a placement new operator in the allocated memory, and we must do it on the device. So we can create this allocate object function above, which basically is a kernel function. It gets as the parameters the pointer to the T it needs to construct and all the arguments, and then it just calls a placement operator new. And you may also note that arguments are passed by value, as these arguments are being passed from a CPU to a GPU, and you can't use any references in this case. And we also have to make this function a free function. It can't be a member function. It's a limitation of CUDA. But the global functions must be freestanding functions. But we can at least use a namespace to make the encapsulation more clear. And then in the constructor of our dev object, we would launch this kernel, but only one instance, only one CUDA thread, and that will do the allocation for us. And now for convenience, we can also add a conversion operator from the dev memory, from the dev object of type T to dev pointer of type T, and we can use it in our functions. And in a similar way, we can also implement the destruction of the object. So we'll create another kernel function, delete object, which basically calls the destructor explicitly, and then the dev memory will just release the memory on the GPU for us. So we've seen the use of dynamic polymorphism. Next stop is new delete. Basically, it's the shortest section in the stock. You just need to know that you can use malloc free and new delete in the kernel code, and it works just as expected. I don't recommend that you actually do it because of the performance, but it's possible and it works. And once we talk about the memory, you may want to look a bit deeper. So it's not related directly to the C++ aspects of CUDA, but as C++ developers, we would like to talk about memory. So let's see what's happening in this case. So this is a snapshot of Nvidia Visual Profiler. I'm not sure that you can read all the names, but basically the blue bar on top is the CPU side of the processing. These are the library calls and the launches that we do in our main function, and we can measure it on CPU side. And now the green ones are basically the copying of the vectors A and B from the host to the GPU. And then the red part, the small one, the add something, is our add kernel. It's the actual work which we perform. And then on the right side, we copy the result back from the GPU to the CPU. So in this case, the portion of the actual processing is very small, as we use a very simple algorithm. Of course, the ratio can be different for different algorithms. But we still want to get better than that. And in this example, the copy and the processing are asynchronous. And with CUDA, I believe that in most of the devices, you can do the copy and the compute operations in the same time. But still sounds as a problem, as before we do any computation of A and B, we need to copy them first to the GPU. So in order to solve this problem, we can take our A and B arrays and break them to chunks. And then we'll process them all in some for loop. And for example, in each iteration of the loop, we'll first copy a chunk K of A to the GPU. Next, we copy a chunk K of vector B to the GPU. And now we can start in parallel, both to process the chunk K on the GPU and also to copy the next chunk to the memory. And then we achieve basically the best performance, which would be the max of copy and compute times. And for that, we would need to use a CUDA memcopy async. And the important note, it requires the memory on the host to be a pinned memory. And also, it makes sense as the copy operation is asynchronous, and it needs to make sure that the memory is not swapped out from the active memory. And we can pin the memory either with CUDA host alloc, which basically would allocate the memory on the CPU as a pinned memory, or we can take an existing memory and pin it with CUDA host register. Another magic feature in the CUDA package is zero copy memory. Basically, what you do, you first you also need to start from a pinned memory, and you can use the same function as host alloc, host register. But now you also need to provide a special parameter to register it as a mapped memory. Then we need to call this getDevicePointer function, which basically takes the pointer to the CPU memory and returns us a pointer to GPU memory. And now we can launch our kernel safely. And in the most recent, I believe that basically in all the existing versions of the GPUs, of the CUDA GPUs, it also supports a unified virtual addressing, which means that basically you don't need to call this getDevicePointer function. Device pointer is exactly the same address as the host pointer. So it sounds very easy to use. But now if we look at the performance, as we see that if the previous example of the async copy took us 2 milliseconds, that now we are up to 70 milliseconds. So the zero copy comes with certain cost, as we can see. And the next feature, basically it's most recent from the CUDA 6, is a unified memory. And just don't be confused between the unified memory and unified virtual addressing. They're totally different features. So unified memory, you allocate it with CUDA malloc managed, and you have to allocate the memory as such. You can't take an existing memory on the CPU and somehow make it managed. And then I'll describe the process in a very, very high level. For example, we have the data in host memory, like our A vector. And now when the device code, our kernel, will try to read the memory, it will get a page fault. And then the page will be migrated, which means copied from the host to device, and it will become unavailable on the device. So all migrations of the data are based on the page faults on both sides. But now if we measure it, then the performance is even worse. And But I must know that for unified memory to have much more control, there's some special functions like prefetch async. You basically tell to CUDA to start copying the memory in advance, or mem advise, which advises the driver where the memory should be located initially. I think that these functions are a bit of a cheating, right? As we wanted a unified memory, but now we're going back to control all the performance. And also, I just want to say that I tried it on basically on desktop computers, on this laptop, and also on some gaming machines, but not on high performance machines like IBM PowerPC. So the results may be different on different hardware. So just to summarize it, the performance, as we sort of expect, is best when we do the hard work of the copying by ourselves, and the simplicity would come at the price of performance. Just to pay attention to this last column of sparse access, it's an interesting use case when you only access a small amount of the data, of the input data, and you don't know in advance which data the algorithm will access. Then there are clear advantages to zero copy or unified memory approaches, as they will copy much less memory than you would do otherwise. So memory is hard. Okay, so going back to C++ features, next feature, which is very useful and very important, is a Lambda. So we'll start from very basic, very simple Lambda. In our kernel code at kernel, we create a status Lambda op, which indicates the operation, and we invoke it in place. And we can also add capture parameters to a Lambda. In this case, we're capturing both vectors A and B, and also the index. And again, it works exactly as you would expect in the CUDA code. But I think that the most exciting use of the lambdas is the fact that you can pass the lambda as a parameter from a CPU to a GPU. So in this case, in the main function, we create a lambda. You can note a special device keyword, which is a CUDA extension to a standard lambda syntax. And then this lambda indicates an operation of sum A plus B. And when we launch the kernel, we just pass it as a parameter to a kernel. And for that to work, you also need to specify a special compilation flag, which basically adds the support to the extended lambda syntax. So now we have this lambda object, which passes the border between the CPU and the GPU. And the question is, what can be captured inside the lambda object? So the first thing that we can capture is we can capture objects by reference. And again, it makes sense. We know that the memory in CPU and the GPU is distinct, and we can take any pointers from CPU and move it to a GPU. And that will fail in the compile time if you try to do it. The more interesting case maybe is the capture of this pointer. So let's see an example. So now our sum operation is a bit more complex. So instead of making a sum of A and B, we want to also add some constant value I to all the elements. So create the structure op, which holds basically the I, which we would like to add to all the cells in C. And we create the lambda, which does A plus B plus I. And we launch the kernel with that lambda. The problem with that code is that it compiles, but it fails in runtime. And the reason is, again, that this pointer was captured by the pointer. Right? Basically, this is a pointer. And to solve it, we can just use special syntax to capture this by value. And now it works fine. So we have our struct. It creates a lambda inside, and it can launch the kernel with a lambda. But still, this looks like a problem from design perspective, right? All we wanted to do is to create a struct which represents a simple operation of A plus B plus I. But instead, it has this apply function, which knows the name of the kernel, and has all these template parameters. Instead, you'd like to do something like that. You'd like to abstract, to basically just create the operation as a Lambda, and then want to somehow use it when we launch the kernel. Let's try to do it straightforward, to take the Lambda from the struct and send it to a kernel function. And the problem is that it fails in compile time because we can't return an auto. We can't return a Lambda, an extended Lambda, as auto from the function. And that's a limitation also in the CUDA compiler. For regular CPU code, it works fine. But with CUDA, we need to do some tricks to make it work. Okay, so next attempt is instead of returning auto from make op, we want to return some specific type. So we can try to return a std function which takes two ints and returns an int. And that it also fails because we can't use std function in the kernel code. It makes sense, as we know that all the functions which are invoked in the CUDA code should have this special device keyword, and there's no reason why a stud function will contain this device keyword inside. But happily, we can use instead a special version of the function from the Nvidia package. So we include env functional instead of functional, and we return env stud function. But now the code compiles, but again, it fails in runtime. And the reason is that we can't pass an env stud function between the CPU and the GPU. It also makes sense, as probably the env stud function is implemented in terms of virtual functions, and we know that we can pass this between the host and the device. So the only solution that I found is basically to send the whole structure op to the kernel, and then inside the kernel, it can call the make op operation, get back the env stud function, invoke it, and now it works. It's a bit uglier than what we wanted it to be, but it works, and it might be useful in some cases. Okay, so we've seen the use of Lambda on the env stud function. But the question is now, are all these zero overhead abstractions as we like it to be in C++? So one approach might be to do some profiling on the code. It is hard to profile the code to this granularity of the results. So instead, we can use tools like Compiler Explorer, and starting from recent versions of Compiler Explorer, it supports CUDA compilation. Basically, we can write our algorithm as a simple C function or use all the C++ features. And we can compare, on the right side, the result of the compilation. We can, and in the all C++ abstractions, basically we expect to see exactly the same binary code between the handmade simple C and the full C++ code. And another tool which comes as part of the CUDA package is CuObjdump. In this case, it works on an object file, and you should use a special flag SASS, which means that you want to see the binary code. And again, you can compare different versions of the functions, a C version and a C++ version, and make sure that basically the binary is exactly the same. So in the tests that I did, I've seen that static polymorphism is zero overhead as we expect. Same goes for Lambda. And even in this example, the use of the env stud function also produced exactly the same binary as the regular C code. I believe that in some cases, like with the regular stud function, it may add some overhead, but at least in simple example, the optimizer managed to remove all the overhead. Okay, so now just to mention other features of C++ which you can use in the CUDA code. So we've seen the use of auto. You can use constexpr. You can use a range-based for loop. And you can use all the R-value semantics, move. It all works in the CUDA code in the same way as in the regular C++ code. The only exception to this rule are the exceptions. And also, it should not surprise us. It's very similar to what happens with embedded C++ code. But we can use most of the features, but not the exceptions, at least not in their current form. It might be that in a standard or two from now, you'll get a new support for exceptions, which are more applicable to embedded code and to CUDA as well. Okay, so now to a couple of features which are specific to CUDA C++ support. So let's look at the first example. We have this kernel, which needs to loop over a certain range of data. And to make it run faster, we like to use the pragman roll statement. And in some of the tests which I've done, it really helps to boost the performance of the CUDA kernels. And until the recent versions of CUDA, you had to specify a hard-coded value to the pragman roll. In the recent versions, you basically use any value which can be deduced in compile time. So in this case, the value that we supply to pragman roll is the result of a constexpr function, which operates on a template parameter and some predefined value. So basically, any value which can be deduced in compile time can be used as pragman roll parameter. The other feature of CUDA is CUDA Runtime Compilation. And if you have been to previous talk, I talked about runtime compilation of C++. So with CUDA, it's part of the package. It's supported out of the box. And it has a number of advantages, like a clear advantage that you can tune your compilation flags based on the real environment. So in runtime, we can check, for example, which GPU our system is using, and then tune the compilation flags to use the appropriate architecture and other flags. But the more C++ aspect of runtime compilation is the ability to select template parameters in runtime. And let's see like another example. So we have this process function, and we know that we want to use pragman roll, and we get the unroll factor as a template parameter to the kernel function. But the problem is that in the main function, we only know the value for the number of layers which you want to run in runtime. We can only know it dynamically. So how can we invoke this kernel function? One solution might be to add a proxy function, which will basically switch on all the possible values of number of layers and would invoke an appropriate template version of your function. It works, but first it's much more code. It requires you to know basically all the values for the layers in advance. It also means that all the versions of the process function have been compiled and added to your binary. So instead, we want to use this runtime compilation feature, and let's see how we can do it. So basically, it gives a brief overview of the process, and all the functions are very well documented. You can look at the CUDA reference. But in general, the first step is to load our source code and all the headers into buffers. And this is a simple operation. It does not require any special support from CUDA. You can just load your files, or you can even build your program on the fly. And next, we use that nvrtc create program, which basically takes the buffers and registers them as a CUDA program. Now, the next step before we can compile our program is to specify all the instantiations of the template parameters in order for the compiler to know which versions of template it needs to compile. And for simple cases, we can just build the string by ourselves. The process 10 int it's a very simple use case. But what if we have some more complex type like thrust vector? So the string that we had to build is the one below, and there's some even more complicated cases. So to help us, we can use a function getTypeName, which basically is templated by the type which you want to add to a function expression, and it builds the name for us. So we can use it to build the template instantiation name as is needed for our use case. Okay, so now we have all the template functions registered, and we can go on and compile the program. The output of the compilation is basically a buffer of the binary code in CUDA internal PTX format. So next, we should load these bits to the GPU, and we need to find the function inside the binary which we need to invoke. And that's easy for the C functions, but for C++ functions, we need to do the mangling of the names. But also, it's very easy. As part of the package, we can use a special function getLoadedName, which takes a name of the function as user would see it. And we need to use the same name of the function as we have previously registered in the add name. And now we can get the mangled name and use it for the module get function. And finally, we can launch our kernel. Just to note that some of the functions start from the NVRTC, which is Nvidia Runtime Compilation, and some are part of CU, which is a more general CUDA package. But again, in the CUDA documentation, you can find all the examples and see how it's done. It's a bit of writing, but it's not very complex still. Okay, just to say a word about thrust. It's part of the CUDA package. It's a template library, and sort of inspired by STL. It has classes like device vector, host vector, which represent the data as vector, as continuous stream of bytes. And it has many algorithms, which are also similar to algorithms in STL, that can run the processing in parallel on the GPU. And also has a device pointer class, which is very similar to the device pointer as we discussed. But of course, it's much more complete, and you can just take it out of thrust and start using it instead of the raw T pointers in the kernel code. Okay, so finally we reach start using C++ in the CUDA kernel code. Okay, so a couple of references. There's a GitHub repo in which you can find all the examples from the stock and some more examples. I also want to plug our meetup group. And in this link, you can find all the talks, and also have a YouTube channel that you can go in and watch, and some relevant links. So one is a description of the new features in CUDA 8, and it includes a detailed description of different C++ features that were added to the CUDA support. And also, you might be interested in the Cocos library. I'm not an expert exactly to describe it, but basically it's a C++ library to create a multi-platform code which will run on different types of GPUs and also on FPGA devices and so on. So thanks.
Just two quick questions. What does 32 mean in that kernel function? Like at kernel, there's a template parameter 32.
Which one?
Like whenever you call that CUDA function, there's that three brackets and there's 32.
Yeah. So when launch a kernel function, basically it always returns void, and the call is asynchronous. It launches the kernel function on the GPU, but then you need to use special functions to wait for the kernel function to complete. and it always returns void. You can't return any value out of it. You need to use, like in our case, the output was the C vector, so you need to pre-allocate the memory for the C vector on the GPU, and then it gets filled, and you get to copy it back when it finishes.
Okay, and if you could go to the slide number 19, I think there's just a small issue. Just wanted to confirm.
This?
19.
Sorry. Okay. Almost there. Yeah.
Yeah, I think the names allocate elements and bytes are kind of are they the same? So elements returns the number of bytes, right?
In this case, it's just to make the allocation of the memory more explicit. So if you use allocate bytes, it will call the constructor with number of bytes as you provided, and the allocate elements, we call it as n.
Okay, yeah, you pass the essential number of elements. Got it. Okay, thank you.
Thanks.
Hey, so when you decide to return an NVSD function, wouldn't it be possible to return just the SD function by adding also the keywords that specified that to run in the GPU side? Instead of returning the NVSD function, just return the SD function? Just what does it do differently internally?
Well, I wanted the original attempt was to create the Lambda on the CPU and then just send it as an argument to the GPU function. So, like we had even in this example, just find it quicker in the presentation. Just like in this example, we create a Lambda and send it as a parameter to kernel. Yeah. I basically wanted to use exactly the same kernel function, the add kernel as is, but to create the Lambda in a different way on the CPU before we send it to a GPU. Does it answer what you're asking?
I was just to understand if we would add device in front of the std function when we would return the std function, if that would work instead of using the NV std function. Yeah.
Is device part of the type system, or is it?
Yeah.
Well, the NVStud function, I believe that it should contain the device keyword in its operator, in its function call operator. Okay. But you can't add it from outside somehow. It should be in the call operator inside.
Okay, cool. Thanks.
Hi. Just one question regarding one keyword that I noticed in one of your slides. I don't remember exactly which number it was. So you used underscore inline underscore rather than inline. So I'm not sure which is the difference between.
This one. Yeah.
Yes. Which is the difference between this one and the normal one without the
so this
underscores?
Okay, so this one is part of the CUDA special keywords.
Right. But you could have used the normal one as well, right?
First of all, you can just keep that keyword, right? As for the functions which are defined in the body of your class, you don't even need to specify it as inline. I believe that for CUDA compiler, you want to make sure that it's inline. I prefer to add the inline keyword, but I can tell you if it's required, or it will do it automatically without the explicit specifying.
Yeah, because sometimes I'm sure that this code would compile without the underscore as well.
Compile, yes.
But I'm not sure about the impact, or if there is any difference, or.
It will compile, but the only question is the optimization, whether this code will get inline or,
yeah, this
or
is
not.
actually the question.
So I don't know.
You don't know.
I just put it, to be on the safe side, maybe, but yeah.
Okay, thanks.
Hi. Regarding the memory types for GPU access like pinned or shared, as I understood from your presentation, they didn't perform that well, as shown in the
The zero
profiler.
copy and the unified, yes.
Yes.
Shared is a totally different
Okay,
type of memory.
but could you explain like the classical use cases where it would be necessary to use these?
I think that just for simplicity, if you get a multi-GPU system, it may be much harder to trace all the memory location of all the objects. Like so, on laptop, on desktop, when you have a single GPU, I don't believe that there's much use case to do it. As after all, we use CUDA to make the performance better, right? But I can imagine that in much more complex systems, with tens of GPUs, it's much harder to do it manually. So you just want the CUDA driver to handle all the memory on demand and pay the extra performance, maybe.
Yeah, well, just to be clear, we work on the MXNet library. It's open source, uses CUDA a lot. And we have this different like memory storages, and some of those are pinned or whatever. And I never understood the purpose of them, and that's why I'm asking what they are for. So
usability is for sure. I mean, from functional perspective, so there's that use case that I mentioned of a sparse access, right? If you only access a small portion of the data and you don't know in advance which one you will do, so that instead of copying all the data to GPU to only access a small part of it, it will somehow automatically copy less data. Mm-hmm. But I think that in most of the examples, you want to process all the data and to copy to a GPU, and then I would not use not the zero copy and not the unified memory. Like, if the code is not too complicated and you manage to do it without, then I believe that it's the best performance to do all the manual copy operations.
Mm-hmm. Maybe I'll talk with you offline.
Sure.
This line is never going to end. Question, you mentioned that Thrust library provides STL-like containers, like vector. So the CUDA compiler by itself doesn't provide containers, and what other containers we might be able to use?
So CUDA, basically, it's just a way to write, to launch a code on the GPU, right? The CUDA itself, the basic CUDA, does not include any containers. And the Thrust library on top of CUDA, it supports only the vector type. So it has the device vector and the host vector, but not other containers. But still, for many algorithms, I mean, surely for this one, but for many others, it's still very useful to use the vector. Also, the performance, I believe, will be not the same as you can achieve with the manual code. And especially if you take care for all the memory alignment and so on, then often your memory will not be continuously aligned in the buffer, like in the case of the vector. So when you do like the work manually, then you will achieve the best performance. And when you go up, you get the usability and you lose some of the performance.
Thank you.
Okay. Thanks to the people remaining in the room.